let's jump into a few more examples with regards to kind of density and pressure. All right, so here's the first one. So an IV filled with medication that has a density of, okay, so they're provided, it's in metric standard units, is hanging 60 inches above the entry point of a patient. Okay, so that's what we have right there. What is the pressure at the entry point? So if we want to be able to find the pressure, right, so we have the density and we have the height. Now, please remember that here you can very easily use the pressure is equal to the density times the gravity times the height, okay, which is pressure at a depth with regards to a fluid. Now, the only thing you have to be careful with is that 60 inches. Now, the 60 inches, okay, so you may kind of recall 1 inch is equal to 2.54 centimeters. So you can easily change this back up, right? So we want to get rid of inches. So 1 inch, and let's maybe dive right into metric standard. So the centimeters I'll change into meters. So 0.0254 meter. And that would give me what the height is. So if I take this, so 60 multiplied by 0.0254 gives me what that height is, which is 1.524 meters. Now that I have this, I can just take the actual density, so that density is given, okay, gravity, okay, acceleration is 9.8, so I have pretty much everything. So here's my height, I already have it on my calculator, so I'll use it, times 9.8, which is the G, times 0.015 times 10 to the 3, which I'll change right away. Okay, so that's going to be 1.5 right there. So from scientific notation back in, and that would give me my pressure, which is 15,159.228. We want to round to the same number of sig figs as the question has. So it looks like it's 3. So 1.5, 200, and that would be pascals in metric standard units. So that's part A. In part B, so we have how high would the IV have to hang in meters so that the pressure is increased by 15%. So this is a really nice question, and it makes you think. Now, you can do this very easily. You can say, okay, well, we want the pressure to be 15% more, right? So, you can, for instance, do something like this. Since you already have the pressure, you can say, okay, well, 15% more than we have, so that's going to be multiplied by, so the original, okay, plus the 15%, which is going to be 1.15. So the 1 stands for 100% of the original. 15 just stands for the increase. And you would have had what your pressure is. Okay, so this is the 15% increase. And now if you have this, you can say, all right, well, I have the density, okay, I have the gravity, and I can solve for the H, okay, in here. And I can just say H is equal to pressure divided by the density, okay, multiplied by G there in the denominator. So, and that would completely work. So for instance, you can take this and you can say divided by, and 1, I guess it was 0.15 multiplied by 9.8, okay, equals, and there you go, there's your height, which is 1.7526. Get to 3 sig figs, it's 1.75 meters. Now, you don't have to do this, because if you look at the equation, if you're increasing this, right, so if you want to increase this by 15%, well, the pressure is proportional to your height, and your density doesn't change, right? Your medication stays the same, and gravity obviously also will not change. So these things do not change, they're constant. So if you're going to say you want this to be increased by 15%, well then just increase the height by 15% and you're going to get the same exact answer. So for instance, if it was hanging, right, so if your original height there was 1.524, well, increase it by 15%, so times 1.15, and you get exactly the same answer without worrying anything. Now, this is a test of you understanding, having things which are proportional to each other in this case. So that would be it for this example, all right? Here's the second example within this video. So So we have a water fish tank. Supposedly this is a challenge question. It's 50 centimeters deep and spans 45 centimeters wide on its sides. What is the average force that the sidewall needs to withstand? Okay, so this is, also a pretty good question in here. So notice they give us the density. Now right away, I'm going to change this density. Okay, and I'll make it and change it back in, okay, to kilograms per meter cubed. And that's just by multiplying by 1,000 because it's in grams per centimeters cubed. So you should get used to that, kind of going back between grams per centimeters cubed back to the SI standard. Now, although this seems difficult, so if you take, now I'm just going to draw the side of the fish tank. All right, so, so let's imagine, we have this fish tank, okay, right here. Here's that side, okay, one of the sides, and we want to know what the force is on this side, right? So, if you're looking at it on the side view, okay, so I'm just going right against it. So it's 50 centimeters deep. Okay, so if it's 50 centimeters deep, it looks not exactly like this. Okay, so let me kind of proportionally make it that way. Okay, so it looks like it's deeper. So this is 50 centimeters. Or 0.5, okay, of a meter within here. And then it says that it's, okay, so here in terms of its width across, it's 45 centimeters, so, or 0.45 meters, right? So everything in metric standards. And what you would want to be able to do is you want to find the force. Now, the force, at least the normal force, now within fluids, okay, it's always perpendicular, okay, to the surface. So now what that means is that the force itself, okay, you can obtain from the fact that you know the pressure that is equal to force divided by the surface area. So now the surface area we have, right? So this particular surface area, so all of this, we can just multiply 0.45 times 0.5 and we have the area. So this isn't really very difficult for us to do. But we want this force. Now, can we obtain what the pressure is, okay, which is on this entire surface? Now notice this will be on average, right? So on average, because pressure changes as the depth changes. So, all the way at the top, okay, of this aquarium, assuming that it's filled all the way to the top. So the pressure is, at least the gauge pressure is 0 there. And then as you keep going deeper and deeper and deeper, the pressure keeps increasing. And that is because pressure is equal to the density times the gravity times the H, right? So that's what we have in here. So that's what it would have been. And as H keeps kind of going and it gets larger and larger. So then how do you find the average? Well, it's increasing, but it's increasing uniformly. So, okay, so within here, so what we can do is we can actually find, okay, what the pressures are. Now the gauge pressure on top is 0. And then we know what the gauge pressure is all the way at the bottom. So the pressure, this is at the bottom, is equal to, so the density itself, so notice it's water, which is 1,000, times 9.8 times the height. Now the height is going to be 0.5. So we have what this pressure is all the way at the bottom in here. Let me calculate that through. 9.8 times 1,000 times 0.5. So we have 4,900. This is pascals, okay? So that's at the bottom. Now at the top, our pressure, at the top, the gauge pressure is 0 because our depth is 0. So if you want to find what the average is, because pressure increases uniformly as the depth keeps going down in an incompressible fluid, then what you can do is you can just take the two pressures. So pressure on top and pressure at the bottom, add them together, and then divide by 2, and you'll get what the average pressure is. So this would have been the average pressure on the glass, right? Which is pretty much kind of like the middle of the height, okay, that you would have. So that is divided by 2, and that would have been 2,450 pascals. That's on average. And so now that you have this, okay, that's this right here. So you have the pressure, you have the area, you can find the average force. So that's why I guess maybe this was a challenge question, okay, within here. So if I go back in here, so here's my pressure, I want to multiply it by my area. My area is 0.5 times 0.45. All right, so that's just the surface area overall. Okay, and this is what we get in terms of the force, okay, itself. Now this force would have been newtons. So 551 to basically 3 significant figures. So that force, 551 newtons, okay, on average, of course, okay. All the way on top it would have been nothing because there's no pressure there. All the way at the bottom, okay, it would have been bigger because the pressure keeps increasing. So what's actually going to happen is that, you know, if you took a side view, okay, of this, so if you drew this kind of aquarium like this, right, so this is where, you know, this right here is the bottom, then, you know, the actual force is being pushing, okay, on this glass, okay, and obviously the pressure is there. And what it's saying is that on average, okay, right there, this would have been the force that it would have to withstand. But all the way at the bottom, the force increases. So the force is bigger at the bottom, and then it gets less and less and less and less and less until it gets to 0, right? So it just kind of goes gradually, and that's because of the pressure, right? So because pressure is dependent on the depth, okay, or the height within the fluid. All right, so that is it for this example. Here's the next example. This one is really good because it makes you think how to think and how to calculate these pressures at depths. It's not often that people think this way. They don't realize that the pressure, okay, is actually dependent on the depth. Okay, and notice that, you know, we have this container, which is a very weird container. It kind of goes down, right? So you have kind of something like this. So this is filled up right there in this container, right? So it's filled up all the way, okay, with a fluid like so. Now what it's asking us, so here's the density, okay, of the fluid, and then it says find the pressure caused, okay, by the fluid at point A. So this is point A right here, right, all the way at the top, and then point C right here, which is, I guess, all the way over here. And this is where, you know, the trouble comes in, because let's do point A first. So very often what students will see is, because this is all the way at the top, right here, they'll think, oh, okay, when they're calculating pressure, which is the density times gravity times the depth, they'll think, well, right here, there is no depth, right? That is true, okay, with respect to this. However, this is an enclosed fluid. So if this is enclosed completely, then the pressure actually passes through Pascal's principle. So it's going to keep passing in. And we have the pressures at the same depth. So that means the top is actually over here. So this point A is 3 meters below. So we do have pressure there. The pressure at the point A is going to be, so this is 9, 8, I guess I'll change it back right there. That's the density, okay, so that's from right here, and multiplied by 9.8, and then multiplied by the actual height or depth, okay, and this would have been 3 meters. And again, the 3 meters is because here's the top, and this is completely enclosed. So that pressure keeps passing. So it's, you know, it gets higher and higher, and here, okay, this pressure over here is the same as this pressure over here. This is really important. So that means this pressure, okay, and the pressure over here, as long as the fluid is filled out, and, okay, and this is kind of fully out, okay, enclosed in there, then these two pressures are the same. You know, pressure over here is going to be the same as pressure over here. So at every single depth, okay, it's going to be the same. And this is kind of the trick, right, that you have to think about. So let's calculate what that would be. And this is gauge pressure that we're calculating, 9800. So times 9.8 times 3, and there is our pressure, which is 288120. That's going to be pascals, okay, within here. So I was to 2 significant figures. So if you want, you know, you can change this back. So 29 and 4 zeros. All right, but I hope that you understand what that concept is. So that means for part C, oh, sorry, it says 3 significant figures, okay, within the question. So that's 288. So I should be careful there. So we have 288000. That's 3 sig figs. It's just, that's what's in the question. So now for part C, well, I hope that now you don't fall in the same trap, and then you can see that, okay, part C is over here, which is the same depth as over here, which means it is from the top, because that's where you start. You start from the top, okay, and it would be 14 meters below. So if you're going to be doing this for part B, right there, then the pressure at B, so everything is the same, except now this is 14. So that's, sorry, at B. I think it was at C. Yeah, at C, but I wrote B there. Okay, so I apologize. So at C, so we have 2800 times 9.8 times 14, or sorry, times 11. I don't know why I got 14 in there. Oh, it is 14. Yeah, notice I'm falling from my own trap. So 11 because I looked over here, and this is 14 from the top. So it's 14. Good that I caught it. I would have led you on the wrong path there. Okay, so here, this would have been 1, 3, 4, 4, and 5, 6, 0, so to 3 sig figs. All right, so there you have it. That's what would have been the answer for this one. Okay, so there you have it. Okay, so that is it for this example. Now, this example leads into kind of the other example, which is tied into this. So it says, based on just this figure, if the fluid is open to the atmosphere, right? So if it's open to the atmosphere, then what would be the gauge pressure at the absolute pressure at point B this time around? Okay, so this time around it is B. All right. So that means, within here, so let me get rid of this. This was C. And those ones were gauge pressures. Now, the gauge pressure itself, so if this is the atmospheric pressure that we have, then what happens is that the pressure over here, so this is going to be at 1 atmosphere. So this is pushing on this. So that means if you want to know what the absolute pressure is, okay, so what the absolute pressure is, that is equal to the pressure, which is the atmospheric pressure, plus the pressure of the gauge pressure, right? So now if we know that, this is 1 atmosphere, which is going to be 101, 325 pascals. So now we have to find out what this gauge pressure is. Now, gauge pressure is only going to be the pressure due to the weight of the fluid. So this is going to be back to density times gravity times the depth, okay, or the height. So 9800 times 9.8 times whatever that would be. Now this is for B. So I have to kind of go back in here. So you're going from here 0. This is going to be 10. All right. So this is at a depth of 10. So I can take this in right there. And so that calculation would be the gauge. So let's do that first. So times 9.8 and then times 10. All right, so this is our gauge pressure, pascals. So you could round to 3 sig figs, okay, as it states there. Okay, so we can certainly do that just as an exercise. So 9.60, I'm going to do that times 10. 1, 2, 3, 4, 5 pascals. Okay, that's 3 sig figs. And now if you have this, you can add the atmospheric pressure to this, and that would have given us the total absolute pressure at that point. Okay, so that's what we would have had entirely. And so that's pretty neat, okay, to be able, to see that. So you have to add those up together. And again, so to 3 sig figs, 106,000 pascals. Okay, so that's what you would have had over here. All right, so that's another example for us, okay, that we have. And here is the last component, which also has to deal with, okay, so let me go back. Okay, so here's the last example, which deals with the same thing. So based on the figure, if the fluid is closed off from the atmosphere, so like we just literally close it off, and then we put a pressure of 1 kilopascal, okay, is applied at 0 meters. So this actually goes back indeed to Pascal's principle. So this is, let's imagine this is 0 over here, so 0 meters. So what we're doing is, okay, we're removing the atmospheric pressure because we're closed off from it, but we're applying 1 kilopascal over here. Well, 1 kilopascal is 1,000 pascals, right? And now what would be the pressure felt at B, okay, over there? Well, so that pressure, right, if we were passing on the 1,000 gets transferred. So Pascal's principle, you know, the pressure gets transferred within a closed in fluid. So that means we're going to be just passing this pressure on. We've already calculated what the gauge pressure was actually in B. So this is what it was. So I'm not going to redo it again. So we have that. You can take a look at the previous example. So we already know that this is the gauge pressure right here. So that gauge pressure, now we're going to be adding this much to it, so another 1,000, and that would have been the total pressure that we would have had. So not very difficult, because if you add 1,000, you're going to just get this right there, okay? Or okay, if you're rounding this off, okay, to 3 sig figs, or if you're rounding it to 2 sig figs, whatever it is that you like, okay, you can do that. But that's how you would set this up. And that's it. All right. So that finishes the set of videos for this. Okay, thank you for watching. I hope that you found this useful. Bye, everybody.